Yeah, thanks, Aidan. So this is a talk that I gave at the EGU meeting, in Vienna about a month ago. We had a whole session there focused on net zero and what this means in terms of carbon budgets and mitigation pathways. And obviously there's a lot of interest now in stabilized climate simulations to assess what the impacts of 1.5 and 2 degrees of global warming, including if we fail to limit global warming, so what the implications are. And so in this talk, we're going to explore the evolution of the climate at different global warming levels based on millennium length simulations that we have done with the Australian Earth System Model, ESM 1.5. Okay, here we go. I can't change my slides for some reason. Here we go. Okay. So the message from the IPCC is quite clear. If we want to limit global warming to 1.5 or 2 degrees, then we must achieve net zero emissions, and major economies are targeting net zero emissions by 2050. However, reaching net zero, as you know, will require major changes, including carbon dioxide removal, and we are actually a long way off achieving this. So despite the urgency and the strong focus on net zero emissions in policy making, we actually don't have the right framework or experiments available to assess those implications or impacts of a stabilized climate at the 1.5 or 2 degrees level. And most future scenarios, even those under CMIP6, are based on transient projections, and then methods such as pattern scaling or time slicing have been used to assess the impacts at different global warming levels. But these methods don't take slow climate processes into account. So we really need a new set of experiments where, for example, carbon dioxide emissions are set to 0. And we also need the models to simulate the same target temperature. So instead of prescribing the same radiative forcing for each model, which would then result in a range of temperature responses to model differences, as you can see in the schematic on the left, we really need to make adjustments for each model individually. And there are multiple ways of simulating a stabilized climate at a specific temperature target. Approaches range from highly idealized simulations to complex frameworks where equivalent CO2 emissions are calculated based on past emissions and past warming. And we have developed a setup to run those stabilized simulations, and that approach sits somewhere in the middle. So the basic idea is that we branch off from an existing emissions-driven SSP-585 run, then switch to 0 CO2 emissions, and then let the climate evolve. And you can see the simulated global mean surface temperature anomaly on this slide. In black, we have the emissions-driven control run that's only shown here for reference. And then we have the ESM historical simulation in light green, which then continues into the future as SSP-585 in dark green. And then we branch off at various points in time for our stabilization runs. So we have done 7 simulations so far, covering a range of potential temperature targets from about 1.2 to 3.5 degrees. And as you can see, at least in our ACCESS-ESM 1.5 model, we still see a small trend in those stabilized runs, but it's relatively small. It's about 0.3 Kelvin over a 1,000-year period. We can now have a closer look at what this temperature trend or change in temperature looks like at the spatial or regional scale. The slide here shows the temperature anomaly for one of the stabilized simulations where the target temperature is about 1.5 degrees after branching off from the SSP run. And so after about 500 years, the global temperature has increased to 1.6. degrees. After about 650 years to 1.7. At the end of the run, the global temperature is 1.8 degrees. And overall, you can see that this increase in global temperature is mainly coming from an increase in temperature over the Southern Ocean. So once atmospheric CO2 concentrations are high enough and maintained long enough to start the warming over the Southern Ocean, then it will then continue to warm and affect the global climate. And as you can see, this cannot be stopped by net zero emissions. You would probably then require ongoing negative emissions. So in the previous slide, we looked at a trend or change in temperature for a single stabilization simulations, but we can also compare the climate at the same global warming level from different simulations. So here we are looking at 3 different worlds derived from 3 different simulations, but they all have the same global warming level of 1.5 degrees. So the first 1.5 degree world is based on a 20-year mean time slice derived from the SSP-585 simulation. The second world is derived from a stabilized run after about 300 years, and the third world is derived from another stabilized run after about 800 years. And in the plots at the bottom, you can see that although these are all 1.5 degree warming worlds, the regional temperatures look very different. So the temperature pattern is shown here as the difference or anomaly from the PI control run. And you can see that in the time slice from SSP-585, we have a strong warming mainly over the Arctic. And in contrast, in the stabilized runs, we see an increase in temperature over the Southern Ocean and a reduced warming over the Arctic. We can also plot the difference between the stabilized worlds and the time slice, which then highlights those long-term changes a lot better. And you can see that in a stabilized world, we get a cooling over the northern hemisphere regions, mainly over the Arctic and Eurasia, and a warming over the Southern Ocean. And that regional northern southern hemisphere contrast, that is increasing the longer the time scale is for our stabilized runs. So now moving from temperature to carbon, this slide here shows the atmospheric CO2 concentrations as anomalies for all the runs that we have done. There is nothing really surprising here. So you can see that once we switch to zero CO2 emissions, atmospheric CO2 concentrations start to decline due to the continued uptake of carbon by land and ocean. And it takes quite a long time for them to stabilize again. Here you have the net carbon flux for the land on the top left and the net carbon flux for the ocean on the top right for all the 7 runs that we have done. And on the bottom, you have the cumulative carbon uptake again by land and ocean. So positive values indicate an uptake. The ocean is pretty much straightforward. Ocean continues to take up carbon over the whole period. And for the earlier branching points, the ocean becomes neutral towards the end of the 1,000-year period. The behavior of the land is different. So initially, over the first 100 years or so, the land remains a sink and continues to take up carbon. But then instead of becoming neutral, the land becomes a small source of carbon. And it remains a source for a very long time, as you can see in the cumulative carbon plot at the bottom left. And we already started to look at where those changes in the land carbon flux are coming from at the spatial scale. And but you have to average over quite a long period of time before you can see a pattern emerging due to the variability. So here you can see the net flux for the land as an average over the first 200 years on the left for 2 different stabilization runs, and on the right you have the net flux after about 500 years, and again as an average over 200 years. So at the beginning of the run, the mid to high northern latitudes, North America or Eurasia, they are really strong sinks, and after about 500 years, only the high latitudes remain as small sinks, and the rest of the land pretty much becomes a source. So just a quick summary. I presented some first results here from our stabilization runs that we have performed with ACCESS ESM 1.5. And I've shown you that there is continuous warming over the Southern Ocean despite net zero CO2 emissions, and that the land becomes a small carbon source long term. There's a lot more work that we are planning to do, and a lot of research questions that we hopefully can answer with those type of runs. And we already started to look at ENSO and how ENSO might change in a stabilized world. And it looks like that ENSO variability would be reduced according to our results. We're also looking at climate extremes and how they potentially change at different global warming levels. And although the output from our simulations is not, it's not published, we're happy to provide the data if you're interested. And you can also contact us if you want to be involved in any further analysis. And I will stop here.
Fantastic. Thanks, Tilo. That was some really interesting results. Do we have any questions for Tilo at this point? I can see Dave's got his hand up, and then Andy.
Yep. So just wanted to clarify how exactly you went from the declining. You had a decline in the initial case. You had a declining temperature after you switched off CO2, and then you had some adjustment, which meant it was kept stable. So what did you do to make it? Sorry, can you explain it again? How did you keep it steady, the temperature?
Okay, so yeah, so there are various aspects. I only mentioned that we switched to net zero CO2 emissions. But obviously there are other things that we need to consider as well. There is the non-CO2 greenhouse gas concentrations, there's ozone, there's the aerosols, and so on. So you have to make a decision about what you do with them. So what we did is we basically set everything back to pre-industrial conditions. So CO2 emissions 0, but everything else back to pre-industrial. And that's why you see that adjustment at the beginning, the drop in temperature. That's mainly due, I think, to the non-CO2 greenhouse gas concentrations, such as methane. They have increased considerably over the historical period. And if you then set them back to pre-industrial, that really leads to that initial drop in temperature. But yes, you have the aerosols as well. So it's the kind of relative combined effect that you see in the short term. But in the long term, it's really the effect of the Southern Ocean that you see in the long-term temperature response.
So Andy, you're up next.
Oh, I guess I was gonna, since Arian's gone, I was gonna ask you what you're doing with freshwater, particularly off the Antarctic, and how that would change potentially the Southern Ocean response.
I don't do anything in addition to what's handled by the model in terms of freshwater.
Yeah, okay.
Maybe
so ESM 1.5 puts excess snow just in as a in at the edge.
Yeah.
Doesn't have the fake icebergs that CM2 has. It just goes in at the coastline.
Do you think?
Yeah, but I guess, I mean, if you're going to warm that much, you're probably going to get a response in Antarctic melting, and that's obviously a pretty big feedback on the Southern Ocean surface temperatures.
There's probably there's melting of ice, but not of the Antarctic shelf or the ice sheet.
Yeah. I'd also be interested to see the total ocean heat uptake over this course of that millennium. I think that'd be an interesting thing to plot.
Yes. And yes, we're currently looking into that as well.
Cool.
So Laurie's got a hand up. I wanted to say I've got a meeting at 4 o'clock and I actually have to leave. So can somebody close the meeting for me? Laurie, do you mind closing?
No worries. Thank you, Shane.
Yeah, thank you, everybody.
Thank you for sharing. Yeah, I just had a quick question, Tilo. Did you compare with other model or not? Or those are just unique simulation?
So yes and no. I mean, the idea was that this is kind of a framework that others could use as well to run their simulations, but recognizing it's expensive. I mean, running this for 1,000 years is quite an expensive thing to do. In parallel, other groups have done similar things, but not the same. So there is a group here in the UK, and they ran stabilized simulations with the UK ESM version, but they ran it with in concentration-driven mode, which is not really comparable, and you get larger drifts in temperature as well, because you don't have the decline in CO2 as you get in the emissions-driven mode. There is another approach, and Martin has run experiments for that with our model as well. It's called the ARA-MIP, Adaptive Emissions Reduction MIP, and that's a bit more complicated. So you basically, every 5 years, you prescribe emissions, and then you adjust each model individually, and you all get them to agree at the same temperature target. And this is more of a protocol that other modeling centers have done as well. So you get a comparison there. But the approach that we have chosen here, I'm not aware that anyone else has run exactly the same yet.
I guess we'll go to Paul.
Okay, so a couple of questions. Like, Tilo, where did you run the experiments? How long did they take in real time? And like, if it was NCI, like, what number of service units did they take?
Okay, that's quite a lot. There's, I'm not sure if I remember all the questions you asked. So they are currently stored on P73 as a non-CMIP6 output. They are processed in terms of that they're converted to NetCDF, but they're not CMORized, I think. But there isn't.
Just wanted to know, like, did you run the simulations on NCI or somewhere else?
Yes, no, at NCI. Yes.
And like, how expensive was it to run in terms of like elapsed time, number of days, and number of mega service units or whatever?
So it's roughly 1 kilo service unit per year, per simulation year, and you get about 15 to 16 simulation years per day if the job is not waiting in the queue.
Right, and you run it for 1,000 simulation years.
We run it for 1,000 years times 7, because we have 7 different branching points or stabilization levels.
Okay. Yeah, a while.
It's an expensive thing to do, yes. But having in mind that, this is something that, and I just indicated that by other modeling groups doing a similar thing, this is really, there's really a shift in terms of looking at transient simulations and moving towards simulations where we can simulate a stabilized climate. So I think there's a lot more interest now in those simulations. Trying to understand what that means.
Does that mean that there's a MIP for this, or it's not?
Okay. Well, it's in discussion. It's very likely that something like that becomes part of a MIP. It's not clear yet where it will it be part of scenario MIP? Will it be part of a different MIP? I think these are discussions that we are currently having. It's a coordination between all the MIPs. It's not a decision that can be made independently by just a single MIP. There is a scenario MIP workshop in a couple of weeks in Reading that I'm going to, and yeah, I'm sure this will be one of the things that we will discuss there.
Thank you.
Any other question? Actually, I was just wondering if your AMOC was slowing down during the 1,000 years to have this, because I noticed that the warming in the Arctic was becoming less and the had intense warming in the south? Is the AMOC partly?
I haven't looked at it in detail yet, but yes, you're right. It looks like that.
Okay, oh, that's interesting.
Probably need
that's
someone
why I
with
asked you
ocean expertise,
because,
don't we?
Yeah.
yes, that's why I was wondering if other models had done it, and we're also seeing this delayed warming in the south or not, or it was just this model. We found in our experiment that the sea ice seems to respond very, very slowly in the south. Like
It does. It's a kind of delayed response, really. But once you get the response, then you cannot stop it anymore. So that's the kind of, it's different to the Arctic, which responds pretty much immediately and is in line with the kind of temperature as well. Whereas, yes, in the Antarctic, it's very different.
So in our, we did AMOC shutdown experiment on the PI and last interglacial condition. And usually you should see a warming in the Southern Ocean and a sea ice retreat in the Southern Ocean. And after 400 years, we still have no sea ice retreat in the Southern Ocean. If anything, it's increasing, which is a bit worrying. But I wonder if it's a delayed response. I mean, do we have to run it for even longer than 400 years to see something in the Southern Ocean, you think, or?
So Matt Chamberlain, he has done a different set of simulations, which is based on the kind of ZECMIP, Zero Emissions Commitment protocol. It's more idealized, so we only change CO2 there. But it's worth having a chat with him because he noticed a similar thing there as well, this delayed response of the Arctic. But I can't remember at what time scale that emerges.
Oh, you mean Southern Ocean, delayed response?
Yes.
Ocean.
Sorry,
Yeah,
Antarctic,
actually, in the glacial experiment that we have, we see the contrary, right? Because we put CO2 suddenly 80 ppm lower. So we would expect a strong cooling. And again, the Southern Ocean is not doing anything, but it has run much less, just over 100 years. And the low latitude are cooling as the Southern Ocean, just nothing happening yet. Okay. Anyway.
Yeah, I mean, the Arctic response, I mean, because the 1.5 is sort of where we would expect the Arctic to start showing a response. And we saw that obviously in the Arctic paper, the CMIP6 Arctic paper that was written across the community, with the ESM was showing a response already in the Arctic. So you'd expect to see the response in these stabilization runs. The fact that you're starting to see it tipping back is quite an interesting response. I'd be interested to have a look at some of those results in that Arctic. I'm not surprised the Labrador Sea is starting to show a response, because that's where the Labrador Sea cooling is an area where there's some sensitivity in the model. So if we are seeing some AMOC cooling, some AMOC response, that's an area where we would see a response, and that response was with respect to what you were seeing. That was a difference with respect to the SSP 585, where we would see the strongest response in the 585 one. So that change isn't perhaps a surprise in that temperature. And we'd be interested to see what's happening now with that respect to what's happening in the ocean. But the same with that ZECMIP response that Matt saw in the Matt Chamberlain saw with respect to a ZECMIP response. He did see a very strong response eventually take place in those ZECMIP ones in the Southern Ocean. And again, the Southern Ocean is the slowest response initially in all the couple of months we've done across all the CMIPs, going all the way back to the early CMIPs. So yeah, you would expect in a very long millennium long run that eventually you're going to get a strong response in the Southern Ocean. So yeah, it is interesting, and it's what you sort of would expect, and the fact it takes a longer time for the Southern Ocean response, but eventually we'll get a response coming along. So yeah, and again, what's going to happen with Antarctica? So the cryosphere community, there's a cryosphere community group, they will be interested in these ones. But having that interaction with the cryosphere, a full cryosphere, will also be interesting for the stabilization. So I'm on that cryosphere group. So we're talking earlier about who's on different groups. I'm sitting in on that group. Obviously, we're not obviously interaction. Haven't got the interaction yet with the full ice sheet and the ice shelves, and eventually also the icebergs. So that's something eventually to have with those models. So I will be one of those people who, if I'm there in person in Canberra for this meeting in September, will be wandering between different meeting rooms. But yes, the long millennium result ones will be of interest. And what sort of stabilization we eventually get for the climate.
Okay, well, I think we might